Okay, if you can take out your packet number 6. I have a couple of copies of keys of packet 5 and 6. If you want to pick up packet 5, if you're also still working on it, and if you want to work at your own pace, that's fine. It's just in class today, I'm going to pick out problems from packet 6, pages 1 through 15, just for us to get practice with multiple choice, and just going to work through these selected pages. So I'm not going to be able to do every problem from every page, but I figured I would pick maybe problems that I find either have a either higher chance of showing up, or a common type of problem, or maybe something that's more challenging. Again, I have keys for package 5 and package 6, depending on which ones you want to pick up. But today I'm just going to go for package 6. So if you can turn to page 4, section A of your multiple choice is going to be non-calculated. So this is going to be 30 questions, non-calculator. So we're going to practice with non-calculator first. I have it, mine is printed out on bigger print here. You guys have 4 problems, 4 to 5 problems per page. So that's why I have 4A and 4B, just because you guys have it all on a half page. Yeah. Is anyone else missing packet 6, AD packet 6? Okay, so number 11 on page 4. It says let f be the function defined by f of x equals the square root of the absolute value of x minus 2. Which of the following statements is true? You may be looking at this and not knowing exactly what this looks like. Well, we know what y equals absolute value of x minus 2 looks like, right? We know that this is going to be a graph with a vertex at 2, and it's going to form a V. The square root is going to still make it very similar process. There's still going to be a sharp turn here, but even though you may not know that the graph is going to look like this. It's going to have a bit of a curve because of the square root. You do know enough of the absolute value of x minus 2 that we're getting a sharp turn out of it. And if we're getting a sharp turn out of it, we know that it is continuous but not differentiable. So it's connected, but there's no hole, there's no asymptote. So we can just say not which of the following statements is true? Continuous but not differentiable. Answer choice A. Okay, number 12. Using substitution for u equals root x, which is equivalent to the following integral. So u equals root x, we do have to strategically choose which is the better u value. We're not going to let both be the u value. We're going to let just the exponent be the u value because we know e to the u is a better fit, and then we know the root x is going to be what we can save for canceling out. But the other thing to watch out for is after you make your substitution, your bounds are also in terms of u. So the way you can tell is you look at all your answer choices. All your answer choices have u variable, which means that there's an understood representation of the bounds as well. The bounds are also in terms of u, so we have to make that adjustment as well. But I'm just going to focus on going through u substitution initially. So we'll just let the exponent be our u value. Go through power rule. Do some cleanup, cross multiply. Okay, so dx equals 2 root x du. We can make that substitution. So we get e to the u over root x times 2 root x du. It's nice to see that root x cancel out. We know we can go through u substitution if no more x's remain, but we know that the 2 is going to have to remain in our integral. So integral to the u du. Now notice everything's in terms of u. The answer choice doesn't present the antiderivative. It just shows the setup. So everything's in terms of u. My bounds are also in terms of u. So I have to adjust these bounds as well. So the way we adjust the bounds is we convert them to be in terms of u. So this is 1 is right now in terms of x. The 4 is also in terms of x. We're going to plug them into the u assigned variable. So we can say if x is equal to 1 and the conversion for u equals root x, then I can put 1 in for root x, and I'm going to get u is equal to root 1, which is still 1. So in this case, my u value didn't change. My lower bound didn't change. But then since my upper bound initially is x equals 4, and I push it through u equals root x, u equals root 4 is equal to 2. So that is my adjusted new upper bound. So my lower bound stays as 1, but my upper bound changes to a 2. So this should be my answer. Answer choice C. Okay. Number 13. We have a function f defined by a piecewise function. what is the value of the depth integral from 1 to 5 f of x dx? So really, we're just looking for the area under the curve of x minus 1 and 2. But we see that these graphs are going to be taking up different regions on our coordinate plane. So to the left of 3, we have an x minus 1. That's a linear graph that's slanted with a slope of 1. And then another one is going to be at 2, which is going to be just a horizontal line. We could draw it out and just use geometric shapes, but I think it's easier and faster to just set up using power rule. But we know that if we want to span the region from 1 to 5, we know there's going to be a different graph on either side of 3. So I'm going to set it up this way. I'm going to say the integral from 1 to 3. I want to look at the area under the, to the left of 3, I have a graph of y equals 2. And then between 3 and 5, I'm now sitting under a different graph, the x minus 1 graph. So I can do power rule, evaluate bounds, power rule, evaluate bounds, and then I can add them up together. So if I combine like terms here, 25 over 2 minus 9 over 2 is 16 over 2. And then minus 5 plus 3 is minus 2. So this gives me 8 minus 2, which is 6. So I have 4 from the graph of 2 dx, and then I have 6 under the x minus 1 graph. I add those together, and I get 10. All right, questions so far? All right, 14. We have f of x is root x squared minus 4. You have g of x, which is 3x minus 2. Find the derivative of f of g of x. So let's build this composite function first. And then we can find the derivative, and then we can plug in 3. So f of g of x would be inserting the 3x minus 2 into the x of my f of x. So if I want to find the derivative of this is clearly chain rule. I have a function within a function. So let me just get that cleaned up. And then I'm going to apply chain rule. So there's outside, inside. I got to work out here. So chain rule. Outside is that bracket to the 1/2. And the inside is also a nested chain rule here, but I'll take care of that next. So outside's derivative. Outside's derivative, bring down the 1/2, keep everything inside the same. Subtract 1 from the exponent. Right, got to finish power rule here. Bring down the 1/2, subtract 1 from the exponent. And now we're ready for the inside portion's derivative. This is also another chain rule here. So now I'm going to worry about this derivative, which is going to be 2 3x minus 2 to the first power times 3. So there's another inside outside here. The minus 4 just goes away, so we can ignore the minus 4. But yeah, this is basically like 3 different layers here. You got that bracket to the 1/2, you got that parentheses squared, and then finally you got that 3x minus 2, which is producing a 3. So now that we have this derivative mess, we can plug 3 in and see if we can get this cleaned up to match one of our answer choices. I'm going to put this back down to the denominator here. So I'm pushing that negative exponents back down, plugging 3 in for x, 0 minus 3 times 3. Sorry, that's 9. 9 minus 2 is 7. 7 squared minus 4. So we got to work that piece out. See that cleaning up. Square root of 45 has a hidden perfect square inside, which is 9. We know square root of 9 can be brought out as 3. And then 42 divided by 6 is going to be 7. So we're left with 7 over root 5. Let's skip to 16. Okay, a particle moves along the x-axis given by x of t minus a equals t minus times t minus b, where a and b are constants. Which of the following values is where a particle is at rest? So I know sometimes when we see constants, it kind of throws us off because we don't know what to do with it. But just treat this like if it was just x is equal to, t minus 2 times t minus or t plus 5, right? If I asked you to find when the particle is at rest, you would find the velocity. You would clean everything up. You could also go through product rule, but we could expand everything out, go through power rule, and then just treat A's and B's like 2's and 5's, right? So you're just going to expand everything out. So the only thing, it looks a little bit messier because you can't combine like terms as easily, but we're going to pretend like we're just working with 2's and 5's or 3's and 5's numbers, right? So treat A's and B's like you would numeric values. Okay, so I'm going to particles at rest is when my velocity is equal to 0. So let me work my way down to velocity by finding, by cleaning it up, expanding everything out, and then taking the derivative, and then setting the derivative equal to 0. Okay, so here's my x of t. I'm just using this as a way of helping us understand that A's and B's are just numbers, but we're going to go back to this equation and expand it out. So b squared minus bt minus at plus ab. So imagine ab is like 2 times 5, right? Just some number here. So we have our cleaned up position function. Let's find our velocity, which is our derivative. So t squared becomes 2t. bt, imagine this was like 5t or 4t or 3t. It'll just be that coefficient, right? That minus b is the derivative. Minus a plus 0, right? ab goes away because if this was a number, then the number would drop to be 0. Okay, set our velocity equal to 0. Now, if we could, we would be able to combine the a's and b's together and just have it be a number, but b's and a's are unknown constants, so we'll just treat them like numbers that we want to solve for t, right? Imagine if the problem was like 2t minus 5, you would add 5 to both sides and divide by 2. Same thing, you want to just move everything over to the other side and solve for t. So the a and b are both going to come over, and then we're just solving for t here. Divide both sides by 2. Okay, page or next one, number 17. The figure above shows the graph of f. If f of x equals the definite integral from 2 to x of g of t dt, which of the following could be the graph of y equals g of x? Okay, so we know that the relationship here is that we know f is sitting at a level above g. So if I want to get to g, I just understand that it's basically the f prime. So I'm just going to get this going so that f prime is really just the derivative of this expression here. Derivative integral cancel each other out. We're just left with g. So we know that f prime equals g. So what could be the graph of g? So basically, we're asking what could be the graph of f prime? What could be the derivative of this graph? Well, this graph has a slope of maybe 1 or 2 or 3. It's some positive slope, right? So we basically want to have a derivative graph that has a slope of 2 or slope of 1 or slope of 3 all the way across, right? The slope is staying constant at the same value all the way through. So we want something that has a slope of 1 or 2 or 3 all the way through. And looks like the best option is going to be A, because this is a slope of like negative something. This is an ever-changing increasing slope. And this is also a changing slope. These are all changing slopes. The only graph that has a constant slope of 2 for every single point, or 1, is going to be this A. Because if we're looking at the derivative graph, we know that above the y-axis represents the slope value. And we want positive slope. We want everything above the x-axis and the same number all the way through. So the same slope all the way through. That's for choice A. Okay, next up. Find the limits. First thing we do with limit is replace every h with 0 here. So we're just doing direct substitution. If I plug 0 in for h, I'll get natural log of 4 minus natural log of 4, which is 0. Denominator is also 0. So if I get 0 over 0, that gives me the ability to apply L'Hopital's rule. So L'Hopital's rule says take the derivative of the numerator and denominator and then try the direct substitution process again. So natural log of u is u prime over u. So u prime over u. Natural log of 4 is a constant. That derivative will just go to 0. And then h's derivative is 1. So now that we have a different version of our expression, we can reevaluate our limits and see what that gets us. Replace 0 in for h. We get 4. So I get 1/4 divided by 1, which is a real number, which is 1/4. Okay, 19. The function f is defined by f of x equals x over x plus 2. What points on the graph of f have a property that the line tangent to f has a slope of 1/2? So we know that anytime we're dealing with slope, we got to involve the derivative. So we're basically are just going to set the derivative equal to 1/2 and solve for x. So derivative, we got to go through quotient rule. There's no way around it. We can't split up. There's multiple terms below in the denominator. So we'll build out our derivative using quotient rule. Okay, so f prime times g minus f g prime all over g squared. Let me clean this up. So we want to set the derivative equal to 1/2 so we can find the location where this curve is going to experience this particular slope. I'm going to cross multiply and go through my algebraic steps to try to solve for x. To solve for x, I'm going to square root both sides. So I have two different x values. It's either +2 minus 2, which is 2 minus 2 is 0. So that's one location. Another location is -2 minus 2, which is -4. So we have two different locations and two different order pairs. And if I plug 0 back into the original function, I'll get order pair 0, 0. And if I plug -4 in for the x-defined location, I'll get -4 over -2, which is +2. So answer choice C. So we have two x value locations, and here they're just spelling out the full order pair, which we can test out and make sure that these x values are actually producing these y values, and they are. So answer choice C. Number 20. We have a function 2x plus 1 cubed. We have inverse functions. So this is the process that we go through with the chart and the table and working our way around our chart. It says find the value of g prime of 1. So anytime I'm looking for an inverse, I'm always going to put that in the bottom right corner. I know that 1 is the x value of my inverse function, which must mean that 1 is the y value of my f function. So I know this much is true, even without testing out my functions. But I know that everything that I'm working with is on the function side. We're going to find that order pair, find the slope at that point, and then once we find that slope, we can turn around and flip it to get the real solution that we're looking for. Okay, so I'm working with this here. I'm figuring out what order pair is going to fit into that function. But just keep reminding yourself that, oh, that's nice. Normally, we had to plug in and solve, but in this case, they give that order pair to us, so that kind of saves us a step. But normally, I would plug that 1 in for the y and cube root both sides and solve for x. But in this case, they give us that order pair. So we know our order pair is 0, 1, which must mean our order pair for g is 1, 0. If I can find f prime of 0, that's going to lead me directly to the answer that I'm looking for. So let's do f prime of 0. But before I can get to f prime of 0, I first have to find f prime of x. So f prime of x, I'll go through chain rule. Outside times inside derivative. Plug 0 in to get my slope. Which gives me 6. So if f prime of 0 is 6, then the slope of g prime of 1 must be 1/6. The y equals 5 is a horizontal asymptote to which of the following functions? So horizontal asymptote is basically when it's like end behavior. And basically, we're just looking to see, as I take the limit as x approaches infinity, which of these will give me a limit of 5. And we know that if we're approaching infinity, we have a different set of rules. We don't plug anything in. We go ahead and we compare degrees. If degrees are the same, then we take the ratio of the coefficients. So there's no denominator there. This one is going to be 0. This is going to be -5. This is going to be the one that fits because limit as x approaches infinity, 20x squared minus x. We see that if we're approaching infinity, we're comparing degrees. Degrees are the same. So we simply take the ratio of the coefficients. So the degrees are the same. So 20 over 4 is simply equal to 5. Okay, 22. What is the absolute maximum value of f? We're basically knowing that there's a curve to this graph. Absolute max is probably going to be where my graph is going to have at least the relative max. So I first have to figure out, where's my slope going to be equal to 0? And then I got to figure out the y value at that point. So we're going to set f prime equal to 0. And then find our critical points from there. So to find the derivative, we got to go through quotient rule. There's a numerator and denominator involved. So let's build out our derivative. F prime g minus fg prime all over g squared. So natural log of x, f prime times g minus f g prime all over g squared. Okay, let me clean this up and see if I can find critical points to test out. 1 over x times x is just going to be 1. I can set both the numerator and the denominator equal to 0 to find my critical points. So denominator is easy. That's just going to be 0. Numerator here, I'll get 1 is equal to natural log of x. If you want to solve for x, if you know that natural log of e is equal to 1, that's great. But you could also do this. You could also raise both sides with e as the base and convince yourself that e and natural log cancels out. We're just left with x equals e to the 1, which is e. So if we test this out here, f prime. Now 0 is actually going to be undefined because that is going to be an asymptote. But we can still let that be our starting point there. And if I test the value to the left of e, like 1, I'll get a positive number. If I plug value larger than e, like e squared or e cubed, I'll get 1 minus natural log of e squared or e cubed, which is negative. Negative or positive is negative. So I know that there is a relative max or absolute max at e because the graph is only doing this, only rising and falling. So the relative max also happens to be the absolute max. But it's asking for the value, though. So the value is not the x value. It's the y value. So we have to put this back into the original function to get that y value. So back to the original function. So natural log of e over e. Natural log of e is 1. So 1 over e is my y value ordered pair at this point. So maximum value, it's basically asking for that y value. Okay, 23. P of t is the size of a population at time t. Which of the following different equation describes linear growth in the size of population? So linear growth would be, imagine if it was like y prime is equal to 4, right? Where my slope is just going to be like 5 or 6 or 8. So the only one that has a linear slope is A here. Okay. Number 24. We have g of x given by x squared e to the kx. For what value of k does g have a critical point at x equals 2/3? So we know a critical point is basically setting the derivative equal to 0. So we know that that's the big picture here. We want to set g prime equal to 0. And then as we set this up, we should be able to get to the point where we can solve for k. But if we can get this set up, then we can just fill in the missing pieces into our equation and hopefully solve for k. So if I want to find g prime, I got to decide what derivative rule I got to go through. So there's product and a little bit of chain, because that e to the kx, it's like e to the 4x, right? I have e to the u times u prime for that. So I start off with product rule, but inside I'm going to have a little bit of chain rule here. F prime g plus f g prime. E to the kx becomes e to the kx times k. It's like e to the 3x, right? E to the 3x becomes e to the 3x times 3. So we'll just treat that k like we would a number. Okay. Set that equal to 0. That's how we want. That's the process we take to find critical points. Now they tell us that this is at a place where x equals 2/3. So I'm going to go ahead and plug in x equals 2/3 for all the x's. And that should allow me to narrow down and get to the point, hopefully we can solve for k. Okay, what if I set this equal to each other here, or bring them over to opposite sides? The nice thing is I can divide a lot of these things out, right? I can divide both sides by e to the 2/3 k. That completely wipes it out. I can divide both sides by -4/9. That's going to leave me with just a -1. Oh, I messed up here. 4/9. Sorry. This 4/9 on that one is 4. Backtrack. Two x e to the kx equals k squared to kx. Getting k equals -1/3. Is that what you're getting to? My key, I have k equals -3. Let me come back and check on that a little bit later. I'm getting -1/3. Okay. Okay, solving differential equation, page 8B, number 25. So go through your steps. This one is nicely set up. Once you cross multiply, you basically have full separation of variables. There's no u substitution needed. You just have to take the integral. And then plug in your order pair. Okay, 26. Let g be the function with the first derivative given by g prime. Which of the following must be true? Okay, so we know g double prime. Well, if you look at our answer choices, they all have mentions of concavity. So let's find the second derivative here. So second derivative, we can use second theorem because you know derivative of this is going to just basically wipe each other out. Just e to the negative x squared. Basically, that's your second derivative. Or 1 over e to the x squared. Now, if you think about this for a moment, 1 over e to the x squared, doesn't matter what the x is. Could be 0, could be negative, could be positive. This exponent in the denominator is always going to produce a positive value. So second derivative is always positive, which means that we're always concave up. So that should eliminate a lot of our choices here. We know concave down is definitely not our answer choice here. And we know G is increasing because if I were to plug in any value here from 0 to x, basically e raised to any number, even though it's negative, I'm still getting a positive value always. So my G prime is always positive as well. So positive G prime, positive G double prime. So my graph must be increasing and my graph must be concave up. Okay, last one here, number 27. X plus 2y times dy dx equals 2x minus y. What's the value of d2y over dx2? So we know dy dx. If I rearranged it, I can make it 2x minus y over x plus 2y. So if I want to find d2y over dx2, I just have to find the second derivative, go through quotient rule, and then each time y's derivative shows up, I got to go through, I got to involve implicit. So there's quotient rule and implicit here. So we'll plug 3, 0 in for dy dx to get our slope. We'll insert them all in, as well as replace all the x's and y's with 3 and 0. It's a little bit tedious with all these numeric steps, but it'll end up giving us answer choice A. But I can finish working this out tomorrow in class as well. Okay, so hopefully today you guys can finish pages 1 through 15, and that way you're on track to get through this entire packet by Friday. But again, there's no late penalty if you turn your packet in after Friday. All right, come get your phones and you can return back your keys too.